Good morning. Welcome to our Aeronautics Technical Seminar. Today's seminar is on TPS and hot structures for hypersonic vehicles. And our distinguished speaker today is Dr. David Glass. Dr. Glass's technical expertise is in the area of high temperature structures and materials. He has a Bachelor's of Science degree in math and physics, and both a master's and PhD in mechanical engineering. Dr. Glass led the NASA team overseeing the development of the carbon-carbon leading edges for the Hyper 10 Mach 10 flight vehicle. Those leading edges helped enable a successful flight in November 2004. And he also led the Tiger team for the development and testing of a small area repair for shuttle return to flight. Dr. Glass has led the Structures and Materials panel of the Joint Army, Navy, NASA, and Air Force, otherwise known as JANF, Air Breathing Propulsion Subcommittee. He is a key leader with the Air Force Research Laboratory personnel on a national TPS working group, and he's on the steering committee for the annual National Space and Missile Materials Symposium. He currently leads the Materials Integrated Product Team for the DARPA Falcon program, and most importantly, he's a key researcher in our Hypersonics project in the Fundamental Aeronautics program. So without further ado, I'd like to introduce Dr. David Glass, and he's going to give a very exciting talk today. Thank you.
Thank you, Dr. Porter. Good morning. Thank you for inviting me to come and talk about thermal protection systems and hot structures. TPS and hot structures are required for a range of hypersonic vehicles, ranging from ballistic re-entry to hypersonic cruise vehicles, both in Earth atmosphere and non-Earth atmosphere. However, today I will be focusing on air-breathing hypersonic vehicles in Earth's atmosphere. This will include single-stage to orbit and two-stage to orbit accelerators, access to space vehicles, as well as hypersonic cruise vehicles. Next chart, please. Okay, we'll start out with some background on aerothermodynamic heating, followed by a look at some different thermal management techniques to address the high heating that we get in these hypersonic vehicles. Then we'll look at TPS for rocket launch vehicles, followed by TPS for hot structures, TPS and hot structures for air-breathing vehicles. Then we'll take a look at some TPS and hot structure components, followed by look at a couple key technical challenges, and finally some concluding remarks. Next chart, please. The Hypersonics project has as one of its reference systems a two-stage to orbit, TSTO, access to space vehicle. The concept of operations for this particular class of vehicles is graphically shown here, where we have altitude versus Mach number. The two-stage vehicle would accelerate up to some staging Mach number represented by the green area. And at that point, the first stage, second stage will separate. First stage will continue on to orbit with the rocket booster. Second stage will return back to the launch site. These air-breathing vehicles like to accelerate along a constant dynamic pressure. Dynamic pressure is a function of the density of the air times the velocity cubed. Lines of constant dynamic pressure shown on the graph is 100 psf, 500 psf, and 2,000 psf. psf is pounds per square foot. As we fly low in the atmosphere at high velocities, we get higher dynamic pressure and higher heating. One of the challenges for air-breathing vehicles is to balance the desire to fly at a high dynamic pressure, which helps as far as performance goes, but results in increased heating. Next chart, please. This chart shows the heating on a reference 1-foot diameter sphere for three different trajectories. A trajectory flown by a CEV from low Earth orbit, a single stage to orbit air breather on ascent, and the space shuttle orbiter. The heating shown here is not the actual heating that we would see on the vehicle, but actually a representative 1-foot diameter sphere. You could think of this as taking a basketball and flying it through each of these three trajectories. For the CEV, Orion, we notice a very large spike in the heat flux, but a fairly short time. Space shuttle is much longer time. The single stage to orbit is even also a long time, high heat flux. The rocket boost is shown in the dash, which again is the same vehicle, but the actual punching into orbit. For a single stage to orbit, for air-breathing vehicles, the diameter, the radius of leading edges are going to be much smaller than 1 foot. So as we'll see later in the presentation, the heat fluxes will be much higher than is shown here because the heat flux is a strong function of the radius. Next chart, please. Another parameter that's very important is the heat load. If we take the heat flux and integrate that over time, we come up with the heat load. That's the total heat into the system. The heat load is shown here again for the 3 different trajectories for the CEV, the SSTO air breather, and the Space Shuttle orbiter on re-entry. Okay, next chart, please. Okay, we'll now take a look at some of the different thermal management approaches that we can use to address the high heating that we get on this class of vehicles. Next chart. Okay, the areas that we will look at in the thermal management are passive, semi-passive, which includes a phase change, and actively cooled structures, which would include some kind of pumped coolant. Next chart. Okay, the first one we'll look at under passive would be an insulated structure. This would be used for moderate heat fluxes where we have relatively short times. An example is shown in the picture where we have the elevons on the Space Shuttle orbiter. This picture was taken on STS-116. We have surface heating coming in. Radiation is the mechanism to get rid of the heat. We have a little bit of heat that's conducted in through the insulation, but the objective of the insulation is to keep heat from reaching the structure, which remains cool. Next chart, please. Next one we'll look at is a heat sink structure. This would be used for moderate heat flux for short times for a transient situation. Example shown here is with the X-15. The leading edges on that utilize the heat sink structure. Surface heating comes in, is radiated away, and some heat is absorbed by the structure. As I mentioned, this is for a transient short time. If you used a heat sink structure for a long period of time, you would end up getting enough heat in to overheat your structure. Next chart, please. Hot structures, the next approach. This would be used for a moderate heat flux for long times. You could think of we talked about heat load. The heat sink structure would be for a low heat load. Hot structure could be for a higher heat load. You can reach longer time steady state with this. Again, we have the heat radiated away, heat conducted inward. Your whole structure is going to come up to high temperatures here. Next chart, please. Okay, if we have high heat fluxes for long times, we may need to go away from a passive approach to a semi-passive approach. First one here is the heat pipe. Heat pipe could be used for high heat fluxes for long times. An example would be for a wing leading edge, shown here in the photograph, a small example of one. But heat here is transferred by a working fluid to another region of the heat pipe where the heat's radiated away, and again the structure operates hot. Next chart, please. Another approach is ablators. Again, this would be for very high heat fluxes, but for relatively short times. It's going to be single use. Example is shown on the Orion capsule. We can see the ablative heat shield on here. This is the same approach that was used for the Apollo capsule. But heat is blocked by the products of the ablation. The ablator is consumed, so again, it's single use. But heat is also absorbed by the ablation process. And the purpose of the ablator here is to keep the structure cool. Next chart, please. If we have even higher heat fluxes, long times, we may need to go to active cooling. Convective cooling is the first one here. This would be for a high heat flux, again for long times. Example shown, Space Shuttle engines. And the active cooling is, convective cooling is used a lot in propulsion systems. But heat is transferred into the coolant heats up, carries the heat away, and the structure will still operate hot even though it's being cooled. Next chart, please. Film cooling is another approach, again for high heat fluxes, long times. Again, this would be used inside of a propulsion system. For film cooling, the coolant is injected into the flow, usually at an upstream location, usually at a single discrete location, and we end up with a thin, cool, insulating blanket. The structure, again, will reach high temperatures and operate hot. Next chart, please. Transpiration cooling is the final cooling approach that we're going to, active cooling approach we'll look at. Again, high heat fluxes, long times. Example shown here is a thrust chamber. But for transpiration cooling, the coolant is injected into the flow through a porous structure continuously over a larger area as opposed to right at the entrance where we had for film cooling. The coolant decreases the heat flux to the structure, and again, the structure will operate hot. Next chart, please. Okay, now let's look at how some of those different thermal management techniques are applied to some different flight vehicles. The graph shows the temperature versus exposure time. On the top left, we see some reentry capsules, Apollo, CEV, Ryan, and the Mercury capsules, which all used ablators. They had very high temperatures, but relatively short times. X-15 used a heat sink approach, and they were able to do that again because of short times and relatively moderate temperatures. The SR-71 had longer times. So they ended up going to a hot structure. Again, the temperatures were moderate temperatures. Space Shuttle Orbiter is basically an insulated aluminum airframe. And again, the moderate temperatures, a little longer times than we've had before. As we move toward air-breathing hypersonic vehicles, shown here is just representative for a single-staged orbit vehicle, but we're going to need a new approach to thermal protection, and it will include a wide range of different approaches. Shown out here are hot structures. There would likely be some insulation and also active cooling. Next chart, please. Okay, now let's take a look at some TPS that's used for some rocket-launched vehicles. Next chart. Okay, first of all, look at the Space Shuttle Orbiter. Again, the orbiter is conventional skin stringer aluminum aircraft structure. The structural temperatures are required to stay below 350 degrees Fahrenheit for reuse purposes. To keep the temperatures down to 350, reusable surface insulation tiles are used primarily on the windward surface. Reusable blankets are used primarily on the leeward surface. For leading edges and the nose cap, where temperatures are going to get greater than, say, 2,300 degrees Fahrenheit, reinforced carbon-carbon is utilized. Next chart, please. The X-33 was a suborbital X vehicle that NASA worked on, that was an X vehicle for a single-stage to orbit rocket system. The TPS on the X-33 was similar to the Space Shuttle Orbiter TPS, except they had metallic TPS on the windward surface. So we had carbon-carbon leading edges, nose cap, chin, and skirt, blankets on the leeward surface, and then metallic TPS on the windward surface. Next chart. Okay, now let's look at TPS and hot structures for air-breathing vehicles. We'll contrast them now. Next chart. Okay, for an air-breathing vehicle, the aerothermodynamics, propulsion system, and airframe, which includes a lot of TPS and hot structures, are highly integrated. Okay, next chart. Okay, what we're going to do now is take a look at rockets and air breathers and see how they differ, and then how that affects and impacts how we deal with thermal management and TPS. First of all, let's look at flight in the atmosphere. Okay, rockets accelerate only. They're usually vertical launch. They get out of the atmosphere quick. They're up and out. Okay, and they generally have a low dynamic pressure. We talked about the dynamic pressure earlier. Air breathers, on the other hand, accelerate and they cruise in the atmosphere. Okay, they are usually horizontal launch, and they have a high dynamic pressure because they fly at high velocities low in the atmosphere to capture the air for the engines. Next chart. Okay, how about drag? Rockets, high drag is not a problem on ascent, and it's actually desired on descent for deceleration. Air breathers, on the other hand, they are optimized for low drag. As a result, they have thin, slender bodies and low thickness to chord ratio. Next chart. Okay, weight and volume is another difference between rockets and air breathers. Rockets are extremely weight critical. Structural mass fraction somewhere on the order of 10% to the gross takeoff weight. What this means is that if you add 1 pound of structure to a rocket, you're actually going to add around 10 pounds of weight to the total system. Air breathers, on the other hand, tend to be more volume critical because volume is what impacts the drag. The structural mass fraction is around 30% of the gross takeoff weight. Now, weight is also very important for air breathers, but the drag, the volume is what drives the drag. Next chart, please. Okay, how do those different factors impact the TPS? Okay, on a rocket, we're going to be driven by descent, low ascent heat loads due to the short ascent time and trajectory. Air breathers, on the other hand, are driven by ascent, descent, and cruise, and we're going to have a high heat load due to the long ascent time. Next chart. Okay, as far as leading edges, on a rocket, leading edges tend to be blunt due to the desire for a high descent drag and also low heat flux. Air breathers, on the other hand, can end up having sharp leading edges due to the desire for low drag and low thickness to chord ratio. We're also going to have high heat fluxes because of the sharp radius. Next chart. Okay, structures. For rockets, the propulsion and airframe are not highly integrated. We see here an example, and the engine is at the back of the vehicle. For an air breather, the propulsion and airframe are highly integrated. We're going to have hot wings, control surfaces, and we're also going to have thin cross sections and high heat flux and high load. The entire undersurface of the air breather vehicle, in the example shown here, is part of the propulsion system. Next chart, please. Okay, these differences provide a lot of thermal structural challenges. Some of these are unique to air-breathing vehicles. Some of them are also present in rocket vehicles. But one of the first thermal structural challenges is large thermal gradients. If we have a cryogenic tank, if we're using liquid hydrogen as a fuel, liquid hydrogen is going to be at minus 423 degrees Fahrenheit. The outer surface, the TPS, may be 2,000 to 3,000 degrees Fahrenheit. It's a large temperature difference from the inside to the outside. Control surfaces are going to be hot, and they're going to be connected through an actuator to the actuator inside the vehicle, which is going to be much cooler. We're going to have thin cross sections that are going to be at very high mechanical loads. We're also going to have high mechanical loads at elevated temperatures on some of these structures. The stability of the outer mold line is important. One, for performance-wise, we need to keep sharp leading edges so we can have strong shocks to get the air into the engines. Leading edges, we need them not to ablate, again, to generate strong shocks, but also just for reuse purposes. Steps and gaps can be a problem. If we have gaps, we could potentially have sneak flow, have the hot plasma leaking in, heating up what's below. Steps can, if we have forward-facing steps, that can increase the transition to turbulent flow, which can increase the heating. Thermal expansion in the propulsion system is another issue. On these air breathers, the propulsion system, again, is much of the undersurface of the vehicle, is very long, can grow on the order of inches, and it has to be attached to the rest of the vehicle to allow the growth. Finally, we're operating for long times at elevated temperatures in an oxidizing environment. Next chart. Some other challenges that we're faced are, first of all, affordable. These type of vehicles, these types of structures are not going to be cheap, but hopefully we can make them affordable. Production cost is an important part of that, and the life cycle cost, inspection and maintenance. Damage tolerance is another issue. Low speed impact, such as tool drop or foreign object damage, say on a runway. Hypervelocity impact, weather is another potential issue, and reuse. But all of these requirements move us away from the shuttle orbiter type of insulation to a new approach to thermal protection. Next chart. Okay, history shows us that the use of new material systems helps enable vehicles. We look first at as an example, at the SR-71. Titanium was used here. The manufacturing processes and databases had to be extended to higher temperature ranges to enable the SR-71 to use titanium as a hot airframe structure. X-15 used Inconel X. Again, the manufacturing processes and the databases had to be extended to higher temperatures to enable use on here. The Space Shuttle Orbiter, again, it was an aluminum type of aircraft with ceramic tiles and blankets, which were developed to enable that type of vehicle to be used. So the question is, for hypersonic air-breathing vehicles, what is the potential material system that's going to enable these vehicles? I believe that the answer is going to be ceramic matrix composites. Next chart, please. Okay, some of the required material attributes for this class of vehicles are high temperature capability, 2,000 to 4,000 degrees Fahrenheit, high strength at those elevated temperatures, high toughness, lightweight, and also environmental durability. Next chart. Okay, so what are our material options? If we look at the chart here where we show the specific strength, which is strength divided by density, versus temperature. So what we would like is a high specific strength, which is high strength, low density. That puts us up in the region of the green area in the top right-hand corner. If we look at our metallic options, MMCs, metallic matrix composites, superalloys, titaniums, those have some cases a good specific strength, but the temperature drops off by the 2,000 degree Fahrenheit range. The carbon-sic material, ACC, which is advanced carbon-carbon, silicon carbide, which are grouped together, which we'll refer to as CMCs or ceramic matrix composites, provide us the high strength at elevated temperatures, which is going to be key for this class of vehicles. Next chart. Okay, what is a ceramic matrix composite, or a CMC? It's graphically shown here, where we have fibers inside of a matrix. The fibers carry the load. The matrix is going to what transfers the load, the external load, to the fibers. Depending on the processing technique, we may have a fiber matrix interface coating. That particular coating, when it is present, is very important. It provides a weak mechanical interface for increased toughness and a graceful failure. One of the key components of a ceramic matrix composite is the environmental barrier coating, which helps protect the materials from oxidation at high temperatures in these environments. Next chart, please. Okay, now we'll take a look at TPS and hot structures components. We'll start out looking at leading edges. Next chart. Okay, the figure here shows some typical ascent leading edge heating for a single staged orbit vehicle. Wing leading edge around 500 BTU per foot square second. Nose leading edge around 5,000 BTU per foot square second. We go down to the cow leading edge, entrance to the inlet, and we get up to around 50,000 BTU per foot square second due to an interaction of some shocks. In comparison, Space Shuttle Orbiter around 70 BTU per foot square second, and CEV on lunar direct return around 700 BTU per foot square second. Next chart, please. Okay, so leading edge radius has a big impact on the heat flux. Heat flux is proportional to 1 over the radius. You can see in the figure here, we have a 1-inch radius and an example, let's say 500 BTU per foot square second. As the radius increases, the heat flux drops some. As we get out to 6, 8, 10-inch radius, heat flux drops to, say, half and even less than the 500. However, as the radius gets smaller, which we need to for a lot of the air-breathing vehicles, the heat fluxes increase significantly. Next chart, please. Okay, the sharp leading edges also impact the chord-wise distribution of the heat flux, in addition to the radius impacting the maximum value. Shown here is in red is the distribution around the leading edge for a sharp leading edge for a hypersonic vehicle. The stagnation line would be basically at zero angle of attack, indicated by the red arrow. For a blunt leading edge, such as on the Space Shuttle Orbiter, shown in the blue, the heating distribution is much more spread out around the leading edge. Also, for the Space Shuttle Orbiter distribution, the maximum heat flux is on the lower surface due to a high angle of attack. So these sharp leading edges produce intense, localized heating. Next chart, please. Okay, if you remember back a few minutes ago, we talked about different thermal management options. We talked about passive, semi-passive, which included heat pipes, and active cooling. For leading edges, for sharp leading edges, we have multiple options, and we will utilize all three of these to manage the intense heating. If we look first at the passive leading edges, we're going to have some reuse limit. Below that, which in this reuse limit is represented by the yellow line, below that we can use this passive leading edge multi-use. Above that, it becomes an ablator. It's going to recess, be single use. We would like to use passive when we can, then heat pipe, or semi-passive, then active. As we move down toward active cooling, we're going to have increased cost, increased complexity, increased weight. Next chart, please. Okay, first of all, we'll look at passive leading edges, and how do we deal with the high heat fluxes that we have on passive leading edges. We do that in two ways. One is to try to have high temperature materials to increase the capability of the leading edge. We also want to try to do anything we can to the thermal properties to reduce the temperatures, and hopefully we'll get the temperatures down so they're below the reuse temperature of the leading edges. Next chart, please. Okay, high temperature materials. The silicon carbide based coatings, such as what's used on the Space Shuttle Orbiter leading edges, are good to around 3,000 degrees Fahrenheit. Above 3,000 F, which on these air-breathing vehicles, we're going to have situations where we're above 3,000 F. We're going to need a different class of materials. Okay, some examples are carbides, oxides, diborides, there's some hafnium, zirconium. Iridium is another potential material. Some of these materials, such as the hafniums, zirconiums, could be used as part of a matrix. Some are more appropriate as a coating, such as the iridium. But the thermal properties can also have a significant impact on the surface temperatures. Next chart. Okay, one of those properties is the thermal conductivity of the fiber and the weave. Carbon fibers come in a lot of different grades with different thermal conductivity. We can also weave those fibers with different architectures. Shown here is a 3-to-1 plane weave, 4-to-1, 5-to-1 plane weave. In the 3-to-1 plane weave, we have 3 times as many fibers in one direction as the other, so it's a very biased weave. The thermal conductivity is shown here. For the 3-to-1, we have 90 BTU per hour foot F in the 3 direction and 70 in the 1 direction. And as we move to the 4-to-1, 5-to-1, you can see that the thermal conductivity is increasing. In the biased direction, the 1 direction, the thermal conductivity is decreasing. Photographs show leading edges with the 3-to-1, 4-to-1, and 5-to-1 architecture that were arc-jet tested. The different weave architecture was able to remove the 5-to-1 architecture was able to remove the heat even more than the 3-to-1, and you can see better performance, survivability as we get to the 4-to-1 and 5-to-1 architecture. Next chart, please. Emissivity is another very important parameter that affects the surface temperatures. The radiation equilibrium temperature shown here is a function of the radiation heat flux. This would be for a radiation equilibrium condition where the convective heat in equals the heat that's radiated out, and that's equal to the emissivity, epsilon times Stefan-Boltzmann constant, times the radiation equilibrium temperature to the 4th power. As an example, if the incoming convective heat and then the outgoing heat is around 50 BTU per foot squared second, with an emissivity of 0.8, our surface temperature is going to be around 3,000 degrees Fahrenheit. Okay, if our emissivity is lower, say 0.3, the surface temperature will be driven up to close to 4,000 degrees Fahrenheit in order to radiate away that same 50 BTU per foot squared second. Next chart. Okay, the recombination or catalytic efficiency is another very important parameter. In hypersonic flow, we will have dissociated species. The air will be dissociated. We're going to have some recombination of that flow. The recombination will include the flow. It will also include some species that are coming off the surface. The surface will also serve as a catalyst to increase the recombination in the flow. This recombination can be exothermic, which means it's going to give off heat. That heat's going to come down to the surface, provide more heating to the surface. As an example of one particular reaction, shown here, we have silicon gas, which will be coming off the surface, which is in the coating, reacting with an oxygen atom to form SiO. But that reaction is exothermic and gives off about 605 BTUs per mole. As an example of how that impacts the heating to the surface, have a graph here for an arc jet test at Mach 4 with the emissivity of 0.84. When the recombination efficiency is close to zero, the surface is referred to as non-catalytic. Heat flux there is around 10 BTU per foot squared second. For a fully catalytic surface with recombination efficiency of 1, the heat flux was around 28 BTU per foot squared second. So we see about a factor of 3 in this particular case increase in the heat flux just due to catalyticity. Next chart, please. Okay, another very important property is the thermal expansion. Looking at the top row there, if we have a bar or a beam, a rod, and it's at some uniform temperature T0, and we heat that up to a higher temperature T1, it's going to grow. It's going to grow some length delta L. Okay, it's constrained at one end, free to grow on the other end. Okay, the strain, the growth, delta L over the initial length L0, but the stress in that rod will be 0, okay, because we're allowing it to grow. Okay, now if we constrain it on both ends, and we're just talking about one dimension here, and we heat it up to a higher temperature, the strain now is 0 because it's not growing, but the stress in the rod is E, which is the modulus elasticity times the thermal expansion times that delta T, that temperature difference. Okay, now the next little pictures show one of the real challenges in thermal structures, hot structures. If we have a temperature gradient, okay, again, we're constraining it in one direction anyway, but we have a temperature gradient across this particular beam. Okay, now the strain is non-zero because it's growing, and the stress is non-zero. Okay, so the thermal stress is generated due to material's thermal expansion, some temperature differential, and structural or mechanical restraint of the thermal growth. Next chart, please. Okay, oxidation is a real key factor in any of these structures because we're operating at high temperatures for long times. The passive oxidation regime is where we like to be, like the structures to be. We have passive oxidation, we have high temperatures and high pressures. Okay, if we look at the little equation there, if we have silicon carbide, which is the coating material on the structures, and it's a solid, and if we have a high pressure, it means we have plenty of oxygen. Okay, the silicon carbide is going to react with 2 oxygen molecules, form SiO2, which is a protective barrier to the oxidation. It's a solid. It's going to perform a nice scale on the surface. And we have some CO2 gas that's given off. If we are in a low pressure regime, then we're going to enter active oxidation at high temperatures. Okay, low pressure, we don't have enough oxygen. So for each silicon carbide, it only has 1.5 oxygens available to react with instead of 2. Okay, so it's going to react with the 1.5 oxygens to form SiO instead of the SiO2 we get when we have passive oxidation. SiO is a gas. Okay, it's not going to form a protective scale like the SiO2. Okay, and it's volatile, so we're going to basically be eating up our silicon carbide coating. Photograph is shown here of a pre-test specimen with silicon carbide coating and post-test after active oxidation. So the transition between passive and active oxidation regime depends on the temperature and partial pressure of the oxygen. And staying in the passive oxidation regime is another one of our real challenges. Next chart, please. Okay, what we're going to do now is take a look at the HyperX X43 passive leading edges and see how some of these properties, variables we just talked about were applied on the HyperX. For the HyperX Mach 10 vehicle, the nose leading edge was designed to reach nearly 4,000 degrees Fahrenheit during the very short 130-second flight. Next chart, please. We talked earlier about high thermal conductivity. For the X43, for the Mach 10 vehicle, we used a 3-to-1 plane weave. We used very high conductivity fibers and wove them in an architecture 3-to-1 to help conduct the heat away from the leading edge. Next chart, please. We also used very high temperature materials. We evaluated 13 different materials. We simulated the flight in arc jet conditions. The flight was Mach 10, 105,000 feet. We tried to simulate those conditions. The nose radius was 30 mils. So you can see it's a very tight nose radius. The heat flux for that condition was 1,300 BTU per foot squared second. And the flight here was very short, 130 seconds. The photograph on the bottom left shows a leading edge test article during arc jet testing. You can also see a successfully tested article and one that failed where the coating came off and we had some severe oxidation of the carbon-carbon substrate. Next chart, please. Okay, we talked about thermal expansion. Thermal expansion can cause high thermal stresses. We had that situation on the leading edges of the HyperX Mach 10 vehicle. You can see in the light green the original geometry and the dark green a deformed geometry due to the thermal expansion due to high temperatures. We did some thermal modeling, and the modeling predicted that the leading edges would fail due to the high compressive thermal stresses. And these thermal stresses are due to the constraint of the thermal expansion as it gets hot. Next chart, please. Okay, as I mentioned, we predicted high thermal stresses. Some of the questions that were asked is, would the substrate fail due to these high thermal stresses? And then, in addition to the substrate, we've got the coating on there. Would the coating buckle and would it spall, or would the coating fall off and then oxidize the substrate? Would slotting be required to keep the leading edge from buckling? And if we did need slotting, what kind of spacing would we need? And then would the slotting prevent spalling of the coating? In order to validate and answer the question of whether the leading edges would fail due to compressive stresses, we had to do a series of testing. The testing all validated, confirmed that the leading edges would survive, but one of the key points here was that we were not able to successfully predict and model the compressive stresses in the leading edge and compare that to the flight condition. Next chart, please. Okay, when we have higher heat fluxes for longer times, we may need to go to another approach, and we'll talk about that now with some heat pipe cooled leading edges, which are semi-passive, where we utilize heat pipes to reduce the leading edge temperatures down to the reuse limits of the materials that we use. Next chart. Okay, what is a heat pipe? how does a heat pipe work? A heat pipe is a fairly simple device, basically three components: a container, a wick, and a working fluid. As an example, if you go out in your backyard and you cut off a section of garden hose, say 3 feet long, then you go to your porch and you pull off some screen, you roll it up to, say it's about 3 layers thick, and you just stick that inside of the tube, and then you get, say, a teaspoon of water, okay, and you put that in just enough water to saturate the wick, okay, then you pull a vacuum on it, you seal it off, okay, now you essentially have a heat pipe, okay. If you can make that to get that to work, it would operate, say, a few hundred degrees, okay. For leading edges, we're going to use heat pipes at much higher temperatures. We're going to use very different material systems, but the operation is the same. We have heat coming in, we'll evaporate that working fluid, the vapor is going to flow down to the cooler end of the heat pipe where we don't have heat coming in. It's going to condense, and the wick is going to pump that working fluid back to the hot end, evaporator end, by the capillary action of the heat pipe. Next chart, please. So how do we use heat pipes to cool leading edges? Okay, let's take that heat pipe, and now we'll bend it around a leading edge. So we have, right in the nose region, we have heat coming in, have what we call evaporator region, where the surface temperature is greater than our radiation equilibrium temperature. Heat comes in that region, the working fluid is evaporated, the vapor goes up to the upper and lower surfaces where it condenses, gives up its heat, and is wicked back to the nose region. Next chart, please. Okay, picture here shows a heat pipe in the shape of a leading edge that was fabricated several years ago for an advanced space transportation system. The little picture cartoon up on the top right shows how this particular heat pipe would be utilized and how it would fit on a leading edge. This was a Hastelloy-X superalloy container. We used sodium, which is a liquid metal, as the working fluid. The interesting thing about this picture is that you can see the RF coils right at the nose region. This heat pipe is heated just at the nose, right at the curved section there, but yet the entire heat pipe is the same color. Okay, that tells you that it's isothermal. Okay, so it's working as a heat pipe, creating an entire leading edge that's at a uniform temperature when it's only heated just at the nose region. Next chart, please. Okay, during NASP, we looked at carbon-carbon leading edges, which eventually were baseline for the National Aerospace Plane. These particular leading edges had carbon-carbon structure with molyrhenium as the container. That's illustrated with the picture here. We also built 3 leading edge heat pipes that were around 30 inches long. These were molyrhenium embedded in carbon-carbon. Here we use lithium as the working fluid to get even higher temperatures capability than the sodium working fluid. And the heat pipe had a D-shaped cross-section as shown in the top figure. 2 of the real challenges with heat pipe cool leading edges and embedding them in a composite are the material compatibility and thermal stresses. We have 2 different materials at elevated temperatures for long times. When you have that, they're going to start reacting. Okay, so if you have molyrhenium in contact with carbon-carbon, you're going to start forming molycarbides. You're also going to have carbon diffusing through the molyrhenium into the heat pipe, say, to potentially degrade the operation of the heat pipe. That is a strong function of both time and temperature. Thermal stresses is another problem. We talked about that earlier, thermal expansion. The molyrhenium has a larger thermal expansion than carbon-carbon, so it wants to grow. Okay, we don't want that heat pipe to buckle, okay, by the carbon-carbon constraining the growth. But we do want good tight contact thermally in order to get the heat from the carbon-carbon through that interface into the heat pipe. So we have 2 conflicting requirements there. So another challenge for this type of leading edges. Next chart, please. Okay, when we have even higher heat fluxes for leading edges, we may need to go with active cooling. actively cooled metallic leading edges have been built. Some of the challenges here are hydrogen interaction, hydrogen embrittlement, again, different materials at elevated temperatures, and multi-cycle life. Next chart. Where we would like to go with actively cooled structures or actively cooled composites. This will increase our temperature capability, decrease the weight. Some of the materials that we may use are superalloys and refractory metals for tubes to contain the coolant, and a CMC structure. Shown in the images there are different concepts. The first one, inserted metallic tubes in a composite, where we may have a composite, drill out holes and insert some tubes to contain the coolant. We may co-process metallic tubes in a composite. And finally, maybe intimate contact, where we may braze tubes to composite. Next chart. Where we really would like to go is an all-composite actively cooled structure. This will give us the lightest weight, highest temperature capability. Photograph shown there is all composite. Some of the challenges here include optimum through the thickness thermal conductivity. Again, we've got to get the heat from the outer surface through that container, through that wall, into the coolant. The containment to the cooling is an issue. Manifolding, how do you connect that composite structure up to some metallic manifolds? Again, oxidation protection, which is a critical issue. Long life, and again, material compatibility, which when we have different materials at high temperatures arises. Next chart. Okay, now we'll take a look at acreage, TPS, and aeroshell. Next chart. Okay, first of all, we'll look at an insulated structure. Shown in the picture here is Space Shuttle Orbiter, taken on STS-114 as the orbiter is approaching the International Space Station. But the insulator, which are tiles, are attached directly to the coal structure to form the outer mold line. The tiles insulation transfers the aero loads to the structure. We have a strain isolation which is required between the tiles and the aluminum structure due to the different thermal expansion. And these tiles are segmented. Each tile is on the order of around 6 inches square. If you look at the photograph, you can also see the carbon-carbon leading edges. You can see a few of them that are a little lighter color, which are ones that were replaced prior to the flight and have not experienced a reentry yet. Next chart, please. Okay, another approach, which again is an insulated TPS, is a standoff TPS. Here we can have a cold or potentially a warm structure. One of the advantages of the standoff TPS is that the outer aeroshell could be a little different shape than the substructure. But the panels are attached to a standoff to create the aeroshell that you want. We're going to transfer aero loads but not thermal loads to the structure. Again, this is a real critical challenge. And again, this is segmented, but the panels in this case may be around 18 inches square. So next chart, please. Okay, a ceramic matrix composite, or CMC standoff TPS, is represented here, where we have a CMC panel that forms the external aerodynamic shape, an internal insulation. This could be a very efficient high temperature fibrous insulation. We'll have some high temperature seals and some kind of attachment to attach this external CMC to the internal structure. Next chart. That attachment of the external CMC to the internal structure is one of the real critical challenges here. We have to transfer the aero loads, the pressure loads, but not the thermal loads. We also have to be able to withstand acoustic and vibration loads. Next chart, please. Another approach is a load-bearing aeroshell. Here, the aeroshell would carry the aero and vehicle axial loads. Insulation here could be incorporated into the aeroshell or separate, say, below the aeroshell. There's potential here for reduced weight. Photograph on the right shows the DARPA Air Force Falcon HTV-2 vehicle and it's a carbon-carbon aeroshell. Next chart. Another approach is a structurally integrated TPS, where the structural wall carries the airframe loads and insulates the inner structure. That's shown graphically here. It's thermally integrated, has a higher efficiency, lower maintenance. The outer surface is a very robust, high-temperature material. The wall thickness helps provide stiffness, and this eliminates surface gaps and steps, and also provides a low part count. Next chart, please. Okay, now we'll look at control surfaces. Next chart. Okay, first of all, we'll look at some insulated control surface. Some of the advantages of an insulated control surface is it's suitable for very large structures. This would also have minimal thermal expansion issues. The little cartoon up on the top right shows a metal or polymer matrix composite control surface with a tile on it as insulation, which is also shown the picture of the orbiter elevons. Some of the disadvantages here are that it's going to be heavy, little thermal margin because the structure is a low temperature structure, and we're also going to have thick cross sections. Remember earlier we talked about drag and with hypersonic air-breathing vehicles needing thin cross sections. So that's a disadvantage to an insulated structure. Next chart. Another approach is a CMC hot structure control surface. Shown graphically there, some of the advantages here are that this will provide the lowest weight and also thin cross sections because you don't have TPS on the outside of it. Minimal thermal expansion mismatch problems because it's all the same material. Thermal margin, CMC has sufficient strength, stiffness, and damage tolerance for the torsional and bending loads that it would experience. And there's no external insulation here. Some of the disadvantages of this particular approach are high manufacturing and tooling costs for the box structure, for the control surface. And it's going to be challenging for very large structures. Limited repair capability. We also have potential manufacturing risk in case of failure or damage. Do you have to, if you have some damage, do you have to scrap the entire structure if you can't repair it? Access for coating is another issue, also access for inspection and maintenance of the internal areas. Next chart. One approach to a all CMC control surface is to build it in small parts and assemble it. That's what's shown in the photograph here. Some of the features here, this particular carbon-sick control surface utilized carbon-sick fasteners. Also utilized a thin-ply torque tube and box structure and gusset members for load transfer. Some of the advantages to this approach are it's relatively simple tooling. Also, if some components are damaged, they can be replaced without complete scrap of the entire control surface. Some of the disadvantages are tolerance buildup can be problematic in assembly if you have numerous parts you're trying to put together. As example here, you can see a lot of fasteners on this particular control surface. Each one is going to have some tolerance. The buildup of all those tolerances, then when you load that mechanically, you can get a little more free play than you would like potentially. High part count is another disadvantage of this approach. Next chart, please. An alternative approach where we would like to go is an integrated fabrication approach. It's going to have fewer joints, better mechanical performance. Some of the disadvantages are the complex tooling that's required and the associated fabrication expense with that, and risk of damage during fabrication. Next chart. Okay, another approach is a hybrid control surface. Some of the advantages here that it may be more affordable manufacturing-wise for large structures, say for a full-scale vehicle where you have extremely large control surfaces. This may be the most affordable approach. Here, you may not require TPS on the upper surface. You would have, say, a CMC, the leading edge, either leading or trailing edges, and the lower surface. And you could replace that CMC if it was damaged. Some of the disadvantages are thermal growth mismatch between the metal PMC coal structure and the CMC. Again, you've got two different materials. Thermal expansion is an issue. Weight increase over an all CMC control surface, and insulation of the box structure could lead to reduced thickness and a smaller moment of inertia or a thicker cross section. Next chart, please. The X43 utilized a hybrid control surface on the leading edges control surfaces. The Haynes 230 was used as the structure with the carbon-carbon leading edge. There was no insulation or controls on the control surface. There was a spindle shown here which connected the control surface to an actuator inside the fuselage. This was a relatively small structure. The carbon-carbon leading edge was on the order of a little over around 2 feet. Next chart, please. Okay, now we'll take a look at a couple of key technical challenges. Next chart. Okay, CMCs are the family of materials that are going to enable air-breathing hypersonic vehicles. Once we can get this class, this family of materials to the point where we can, with confidence and repeatability, successfully build structures and fly them, they'll be utilized over large areas of these hypersonic air-breathing vehicles. They'll be utilized for leading edges, for acreage, for hot structures in the propulsion system, whether it's passively cooled or actively cooled, for the inlet, for the nozzle. Much of the vehicle will utilize the CMCs. For most hypersonic vehicles, there are two key material structural structures technical challenges to get us to this point. Next chart, please. First one is environmental durability. We talked about oxidation. Okay, this is basically oxidation resistance. Trying to get the mission life, trying to get the number of cycles that we need under combined loads, being able to inspect it, repair it, and being able to predict what kind of life we're going to get. All of those are important. Next chart, please. Okay, the second key technical challenge is fabrication. Okay, we can fabricate small coupons, okay, and most of the time, but not always, we can fabricate them repeatably so that what we build, the coupon we build today is going to be the same that we build 6 months from now. That's not always the case, even for small coupons. But the key point here is that a state-of-the-art material is not the same thing as a state-of-the-art structure. There's a big difference, okay, and that's one of the key things I'd like for you to get out of this talk, is that a state-of-the-art material is not the same thing as a state-of-the-art structure. Next chart, please. Okay, there are a lot of fabrication challenges to go from a small material to a large structure. Thickness is one. If we want to build a thick structure, we need the density, the properties to be uniform throughout the structure. Okay, that's the challenge. Complex curvature. If we want to build a 1 foot square flat panel, okay, we can go do that. Okay, but if we want to build the control surface shown there, or the kind that we actually need to fly, there's a big step there. Going up in large scale is a problem. The challenges that I'm listing here are all process dependent. There are a lot of different processes for fabricating carbon-carbons, for carbon-SiC, SiC-SiC, and each of them have their own different challenges. Low interlaminar properties is an issue, and if you have low interlaminar properties, sometimes you're going to get delaminations. Okay, how do you detect those delaminations, and what delaminations can you live with? Which ones do you have to try to repair or replace? So that's some of the non-destruction inspection that goes with that. Tooling is a very critical, time expensive process. In some cases, we have each part is going to have more tooling parts than it is to generate the part. Assembly methods and tolerances. Reproducibility is another issue. Fabrication modeling of the fabrication process so we can predict how the structure is going to perform and react as it's being fabricated. Design of manufacturable structures. We have to be able to design these structures so that we can make them successfully. Designing a CMC structure is very different from designing a metallic structure. Okay, and affordability is another issue, both cost and getting the schedule so that we can afford the time. Next chart, please. Okay, once we build these structures, we've got to fly them and they have to meet the flight requirements. That's another real challenge, and that impacts the maturity of the structures. So operation has a significant impact on our ability to use these materials and structures on flight vehicles. First of all, thermal loads. If you have a structure and you're operating it at, if you have a CMC, you're operating at 2,600 degrees Fahrenheit, or you're operating at 3,000 degrees Fahrenheit, it's going to perform differently. It's going to have a different life. Okay, thermal gradients is another issue, which causes a lot of thermal stresses. Mechanical loads. It also has to withstand vibration, acoustic loads. We talked earlier about pressure, active oxidation, passive oxidation. If we're flying in regimes where we're going to get close to the active oxidation regime, then that's going to be a real problem. Okay, we have to back off and make sure we stay in the passive oxidation. And then we got to combine all those loads together. Okay, in real flights, you're not going to decouple your thermal, your mechanical pressure loads. And number of cycles. If you want a vehicle to fly 1 or 2 flights, that's a very different vehicle structure than one that's going to fly 100, 200 flights. Okay, next chart, please. Okay, now a few concluding remarks. Next chart, please. Okay, hypersonic air-breathing vehicles will require us to move beyond an insulated aluminum airplane, such as with the Space Shuttle Orbiter, to a vehicle with multiple TPS and hot structure approaches. Our ability to build and fly these vehicles successfully will depend on our ability to utilize multiple types of CMC structures, first having solved environmental durability and fabrication challenges. Next chart. Now, I'd just like to acknowledge the help and support of numerous folks who helped me pull this presentation together. Thank you.
Thank you, David. I'm J.D. Harrington. I'll handle the question and answer portion of today's presentation. Before we get started, if you have questions, and I hope you do, you will wait until the microphone gets to you, and if you'll introduce yourself before you get started. Anyone have any questions here in the headquarters audience? All right, stand by for a moment.
Murray Hirschbein. Early on in your chart, you showed that little green spot in the upper corner, 4,000 degrees and very high specific strength. What material or structural systems do you see coming on board beyond the current ones like carbon-6 that are possibly going to get up in that territory?
Okay, the material systems that will get us up into the 4,000 F range are hafniums, zirconiums, carbides, oxides, diborides of those materials. Iridium will also get us up to, as far as, iridium is not going to be a structural material.
That corner where you have specific strength and high
I think it will be, again, well, carbon will go there, and the carbon fibers will go there. Carbon will go there if you can protect it. Okay, so you got to protect the carbon with some kind of coating. You're never going to get the life, say never, you're not going to get the life at 4,000 F with those material systems that you're going to get at 3,000. But the material systems will be the carbides, diborides, oxides of stuff like hafnium, zirconium. And then iridium as a, potentially as a coating material, but not an outer surface. The catalyticity of iridium would be high. It's going to get soft, so it would be coated, have a coating on it, maybe of hafnia, something like that. But that's a real challenge. That's one of the key challenges. And if we cannot get the life we want up at the 4,000, then we're going to have to cool it or redesign it. If we make the leading edges a little larger, heat flux is going to come down, temperature is going to come down. We may have to fly a different trajectory. in order to, it's the balance between all that. And that's, the folks who design the materials, we always need interaction. Well, the folks who design the vehicles, we need a good interaction with the materials folks so that they don't design the vehicle, give it to the structures materials guys, and then they throw up their hand and say, well, there's no way I can do that. Got to work together.
Okay, any other questions? And also a reminder, we can take questions from the centers if you're in your central specific location. Any other questions here at headquarters? Anyone up here on the right?
My name is Bob McCure. Having worked in the industry for a number of years before coming to NASA, as a stress and vibrations analyst, one of the problems that I had was working mostly with metallics. The problem ductility is a key requirement for all the unknowns. The problem I have with these ceramic materials, they're basically, there is no ductility. And so how do you design a structure now with the metallic structures, integrate with metallic structures to take into account the lack of ductility?
And that's a good question, and there is, it's probably not fair to say there's no ductility, okay? But those are design issues, and we do understand the properties, the mechanical properties, and are able to design the structures based on having extremely low, say no ductility. But when you say how do you, I'm not quite sure how the best way to answer your question. How do you design those structures? I mean, we've got material property databases, okay, and we're able to calculate, from that, calculate what the stresses are going to be and design the structures. And we have successfully fabricated and tested ceramic matrix composite structures, control surfaces, leading edges. The carbon-carbon leading edges on the space shuttle have flown for years. We have not yet flown ceramic matrix composite control surfaces on reusable reentry vehicles. There are ceramic matrix composites that are flying on the flaps and seals on jet fighters. So I think we can and we have successfully built, designed, built, and flown ceramic matrix composites.
All right, any other questions here at the headquarters? Before we began, I had a couple of questions drafted as well. And if I can ask one question, David. You showed examples of the X-43A flight conditions being simulated, showing Mach 10 speeds at about 105,000 feet for about 130 seconds and so. The question is time a limiting factor at this speed and altitude? Will temperatures continue to rise? If you stated that altitude and that, will CMC materials continue to hold up at those altitudes and temperatures?
On the HyperX Mach 10 vehicle, time is a factor, and time is always a factor on these vehicles at high temperatures. For this particular case, we did reach steady state conditions for the nose leading edge, but we are conducting, the leading edge was designed to conduct heat away from the leading edge to keep that temperature down, take the heat back. Leading edge did reach steady state temperature, but as time continued to increase, and if we were to fly a lot longer, we would heat up even further back. We also, the coatings are, in this particular case, did fine, but it would not survive potentially and would have challenges at those temperatures for real long times.
Okay, while others in the audience here think of a question, we'll go to Glenn.
Hi, this is Gary Sang. Very interesting presentation. My question is, can you discuss a little bit about methods for repair of CMCs?
Methods for repairs for CMCs. You can try to repair them during fabrication, and again, that's going to depend on the processing. If we're allowed to lump carbon-carbon in with CMCs, which if we have a ceramic coating on carbon-carbon, then we can call it a CMC. Continued infiltration and pyrolysis can help repair some delaminations. Coatings are one of the big issues that need to be repaired, and field repair of coatings, being able to paint on a coating is, we do have coatings that we can paint on. How well they work and if they're going to continue to operate at the conditions we want is a question, but that would be a real advantage to be able to repair, say, in the field. So I guess it depends, during the process, and it's going to depend on different, what the processing technique is. But the repair is it's not something that we do very well yet, to be able to repair and have the confidence to continue to fly it.
All right, any other questions? Before we conclude, I have one more question. Dr. Glass, how do you see the process of material development and modeling changing over the next 30 years, for instance?
How do you
see the process of material development and modeling changing in the next 30 years?
I think we will continue, modeling will increase, okay, as we're able to more accurately and faster to run models faster down at the micro scale as computer capabilities get better. Oxidation is one example where it would be good to be able to model the oxidation process, actually what's going on, and then once we can do that, to try to attack the particular problems. We still are going to need to fabricate specimens, test them, but it should be will be a joint integrated effort.
All right, last chance. Any other questions here? We have one more here in the front.
Swan Alonso from ARMD. Could you say something about the state of the art in modeling of materials of the kind that you said or you discussed here? What can we and what can we not do, and what's needed?
Short answer is no. That's modeling of materials is not my area. I think it is something that ARMD, the Structured Materials, is working on, and is important. It's important to be able to model what the fabrication process and then how it's going to perform in flight. The oxidation, again, is one of our most critical issues, being able to model that and then from that predict and figure out how to attack the problem. And I know that we do have models at different scales, down at the micro all the way up to the macro, but it's not, in a lot of cases, not at the fidelity, the accuracy that we need. I talked about the example with the HyperX leading edges, and the modeling kept predicting that we were going to fail due to the compressive stresses. But the testing and the flight verified that it did not fail.
All right, and with that, we're going to conclude today's presentation. If you'd like more information about this or any other aeronautics topic, we encourage you to go to our website, www.aeronautics.nasa.gov. And at this time, I'd like to thank Dr. David Glass for today's presentation. Thank you, David.